Okay, today we are starting the final topic in mechanics, that is going to be hydrodynamics. Okay, in hydrodynamics we will be learning the physics behind moving a fluid. Okay, so you can call it fluid dynamics, but okay, I'll go with hydrodynamics itself. Hydrodynamics. So before we get on with the theories, I think we need to first study about certain quantities which we will be needing as we move forward. So under that, the first quantity you will need to know is called volume flow rate. Okay, it's called volume flow rate. What is volume flow rate? We have already studied it, so I'll quickly finish it. Can someone tell me what is volume flow rate? Volume flow rate. We usually use the symbol Q. Okay, where have we heard about this before? Volume flow rate, people, where have you heard about it? Yeah, good. Amount of liquid flowing per unit time. No, I don't like the word amount of liquid flowing per unit time. No, you have to be more specific than that. Your answer has to be more specific than that. What is it? It should be volume of liquid flowing per unit time. Okay, so you can say a simple definition: volume flowing per unit time or per second. It's a volume flowing per unit time. So the word volume is very important. It's volume flow rate, and we have learned the equation. I think under units and dimensions I have explained it. Can you remember? Under when we define rate and gradient, we use this. So volume flow rate Q is equal to volume divided by time. But we very rarely use this equation directly. We alter it this way. Now Q is equal to, instead of volume, people, I can write what now? Area multiplied by what? Length, right? When I multiply area by length, that will give me volume, and then I have to divide by time. Now what is length over time, people? What is length over time? When you divide length by time, what is it? That is going to be, no, length over time. God, no. What is length over time? Come on. What is length over time? Length over time. When you divide length by time, what do you get? Anybody? Velocity. Yes, velocity or speed. Velocity or speed. So I'll say area into speed. Area into speed. So volume flow rate has this new equation, that is area, rather cross-sectional area into speed. Then we can write the equation Q equals AV. That is going to be a very important equation in our in this lesson. Q equals AV. Right. So as a formality, we'll just define them one by one. Volume flow rate. What about the SI unit, people? What is the SI unit of volume flow rate? Volume flow rate SI unit is going to be volume divided by time, meter cube per second. Meter cube per second. And then A is in fact cross-sectional area. All right, don't forget that. Cross-sectional area. What is the SI unit for cross-sectional area? SI unit for cross-sectional area is going to be meter squared. And finally, speed or velocity, V. We'll go with speed because we don't really bother about the direction here, meters per second. These are the three. And as usual, dimensions of Q. Dimensions of Q is going to be dimensions of volume over time, and that is going to be volume L cube over T. Capital L cube over capital T. So that is L cube T minus 1. Good. These are the dimensions and units of each. Okay, that is volume flow rate, people. Similarly, now I'm going to make a slight change to this same equation, and that will be for mass flow rate. Mass flow rate. I can even copy this and make slight changes. I'll do it right away. People, you can copy with me. I think while I write, you also will get time, so that I will make a copy of this one so that it's more convenient to me. The next quantity I want to introduce to you is mass flow rate. Okay, mass flow rate. So let's replace the word volume with mass. So volume here, mass. Okay, mass. Everything must be substituted with mass. After that, I think I will have to make some changes. After that, I'll have to make some changes. Even this equation will be different. This okay. This will have to be changed. This also will have to this we will have to change. Wait a minute, we will explain everything one by one. This will have to change, right? But there's an easy way to get the equation for this one. What should I do, people? Not same symbol. Wait, we don't use the same symbol. I am going to write a mathematical symbol for this. Mass flow rate is given by dm over dt, people. Dm over dt. That is how we define mass flow rate. Change in mass divided by change in time. Students who are doing mathematics will understand it more. We use this in differentiation. I don't know whether you have studied differentiation in mathematics, but others don't worry about it. This is a symbol, mass flow rate. So it's change in mass divided by change in time. This whole fraction is mass flow rate. So if volume flow rate is volume flowing per unit time, mass flow rate is going to be mass flowing per unit time. Then mass flow rate will be equal to not Q. We use the term dm over dt as a whole. That is mass over time. Mass divided by time is mass flow rate. The delta we can use, but this is the mathematical format. Zainab Zanir, there will be we will be using similar symbols later also. In the fourth unit, we will be using dq by dt, d theta by dt. Okay, it's a mathematical term. Physics is based on maths. Without maths, you can't do any analysis in physics. So just let's get used to it. Mass flow rate. We will be using this mass flow rate again in unit 4. So I think it would be better if we learn it in the proper format. Now, dmo dt, the equation is going to be slightly different, people. How can I write mass? Now, mass is a volume into density, right? Volume into density over time. Volume into density over time. Okay. Now, what is volume can be expanded even further. No? Now, mass is volume into density over time, and volume can be expanded even further, just like the previous one. That is cross-sectional area. I'll put CS area, cross-sectional area into here. Even here, it would be better if you write cross-sectional area. Cross-sectional area into length into density. Okay, divided by time. Sometimes they might ask you to derive these equations. And once again, we are going to combine length and time. Once again, we are going to combine length and time, which means we will be getting something like this. dm over dt is cross-sectional area into speed into density, just multiplying volume flow rate by density, that's all. So it's going to be AV rho. It's going to be AV rho, right? Okay. For volume flow rate, we use Q usually. Now you can use dV by dt, but it's rarely used. We directly use Q for volume flow rate. Then people, finally you will arrive at an equation like this, dm over dt. It's equal to, for cross sectional area, we usually go with A, speed, and density we usually go with rho. So it's going to be AV rho. If you turn back your unit 1 exercise book under dimensional analysis, we have derived, I think we must have derived all these equations at some point. We must have got these equations during dimensional analysis. Okay, so let's define them one by one again. dm over dt is the mass flow rate. What is the unit of mass flow rate, anybody? What is going to be the unit of mass flow rate? SI unit. What is going to be the unit? It's going to be kilogram per second, right? Kilogram per second. It's going to be kilogram per second. And one more quantity must be defined additional, that is density. Density, kilogram per meter cube. And then the the symbol, I mean, not the symbol, the dimensions of mass flow rate, that is dm over dt, mass over time, in capital M over capital T, mt minus 1. That is going to be the dimension. Okay, right. So this, especially both the equations are going to be important. Yeah, both are important. I'm not going to say who is more important. Both are equally important. We will be using this for certain questions. We'll be using this for certain questions. Good. Right. Okay. So now I'm going to take you back to Newton's laws. Okay, I'm going to take you back to Newton's laws. There are now. Can you remember we use Newton's law, Newton's second law to understand certain things? For example, Newton's second law and third law. No? For example, when you want to jump, okay, when you want to jump, it happens as a combination of Newton's second law and third law. You push the earth down, earth pushes you upwards. That is Newton's third law. How much force you get from earth, how much force you get from earth, or else at what speed you're going to leave earth, that will depend on Newton's second law, using force equal to change in momentum over time. Okay, likewise you can apply Newton's second law for flowing fluids as well, flowing liquids as well. That's what I'm going to teach you next, and based on that we will be able to understand the motion of a helicopter. How does a helicopter take off? How does a helicopter move forward? How does a helicopter move in a circular path? All these things we will be learning based on that. Okay, so I'm going to teach you something very interesting now, that is force created. Next topic, force created by or on a flowing fluid. I'll say fluid. Fluid means what? What is fluid? Fluid means it could be liquid or gas. Could be one of them. We don't have to restrict it to only liquids. Right. Now, I'll just say put an arrow, Newton's second law. I hope you all can remember Newton's second law. So we are going to combine that with Newton's second law. So let's see how it works. Even this equation we have derived under dimension analysis. See if something rings a bell. According to Newton's second law, you know, resultant force. What's resultant force? We write an equation. Resultant force is equal to anything flows is fluid. Yeah, anything that flows is fluid. So liquid and gas can flow. No? That is a fluid. Resultant force is equal to change in momentum, change in linear momentum over time. Change in linear momentum over time. So you cannot forget this equation, people. Basics. And then for resultant force, I can put F. For change in momentum, I can put mv minus mu over t. And I'll take m common, people, this time. By taking m common, we derive the equation F equal ma. When I take m out, v minus u over t is acceleration. But this time we're going to do something a little different. M is out, v minus u, and in under m I'll put time. So what is m over t now? You know m over t now in a different way. What is m over t? What is m over t, people? You know this. Come on. It is mass flow rate. Very good. It is mass flow rate. Good job. Mass flow rate. Mass flow rate. Okay. Or in other words, just like some of you have said, dm over dt. Exactly. Right. Now, instead of dm over dt, what can I write, people? But we know dm over dt is equal to, we just derived an equation, AV rho. So I'm getting an equation like this then, F equals, instead of M over T, I can substitute AV rho inside the bracket V minus U. Inside the bracket V minus U. Okay, right. There are instances where liquid will be initially at rest, people. So you can say, if the liquid is initially at rest, if the fluid, okay, if the fluid is initially at rest, what will happen? The fluid is initially at rest, who is zero? If your fluid is initially at rest, air or water for that matter, V is going to be zero. Initially, no, U is going to be zero, no? U is going to be zero. Initial velocity is zero. So what is F? F is going to be AV rho V minus zero. Then people finally arrive at an equation, F equals AV squared rho. AV squared rho. Okay, so done. That is how it works. Is that understood, people? So whenever you get a question based on a fluid moving, you will be using this equation here of in future, AV squared rho. But sometimes you might not be using that directly, but better to start this way, the way I started it. If the liquid is at rest initially, then you can use this equation. Now, for example, helicopter. If you take a helicopter, the air below the helicopter is at rest. Suddenly, when the blade starts rotating, the air is pushed downwards. Suddenly, the air is pushed downwards. So, for situations like that, we can use this equation. When a helicopter rotor, the blades they rotate, helicopter will push the air down. If you take your fan, ceiling fan, think of the ceiling fan, will you? When you sit under the ceiling fan, what happens? The ceiling fan is pushing the air towards you, doesn't it? The ceiling fan is pushing the air towards you, just like that. In helicopter, the fan will be pushing the air down. Air will push the helicopter up according to Newton's third law. That's how the helicopter goes up. Okay, there we will be incorporating Newton's second law and third law as well, both. Right, looks like my mic has yeah, so rocket and helicopter, same scenario. Am I not audible enough, people? How about now, Ruksha, can you hear? My audio input is fine, it's not reduced. Okay, right. Anyways, so this is how it goes, huh? Right. So this is the next theory part. Now we have studied three equations all of a sudden. Q equals AV, dMO dt, mass flow rate is equal to AV rho, and the flows created on or by a fluid, a flowing fluid, is given by AV squared rho. How to use this equation, we'll discuss about that soon. Right, now maybe we can start with a question, people. Quick question. Give me a second. Yeah, we'll start with a quick question. Okay, let me take a screenshot of this one. Done. And let's do it together. Hint, try to start from the scratch and do it. Okay, here we go. The question. A-level final paper, these kind of questions are a bit rare, but they will ask. A water jet is ejected. A water jet is ejected out of a tube. Of cross-sectional area 30 centimeters square at a velocity of let's say 5 meters per second. Okay, right. This water jet strikes a nearby vertical wall vertical wall, vertical wall in horizontally. I mean, the word horizontally describes how the water jet is striking the wall horizontally. This wall is vertical, water jet is hitting it horizontally, and recoils. What is the meaning of recoil, people? I think this is not a new word to us. And recoils horizontally. Recoils means rebounds, bounces back in the same direction. Okay, retracting through the same path exactly. Bouncing back, but to the same path at a velocity of 3 meters per second. The velocity of 3 meters per second. Okay, why 5 has reduced to 3? What's the reason? Anyone quickly can you tell me why it's striking at 5 but bouncing back at 3? There will be loss of energy, so you will not be able to get the water recoiling at the same. Sometimes in questions they might give you equal velocity. It depends, not equal velocity, equal speed, so it depends. Then the question is, what is the force exerted? What is the force exerted? What is the force exerted by water jet on the wall? Okay, what other information should I provide you? What other information should I provide you, people? And I should provide you density of water. Very good, yeah. So density of water, as usual, take it as 1000 kilogram per meter cube. Do you want to try or shall I explain? Right, okay, give it a try then. Yes, let's see. This you can't directly use AV squared rho equation here. You have to think a little bit and do. That's the hint I can give you. Start with Newton's second law. We have done questions like this, people. A bat ball approaching a bat and hitting. When you hit the ball, what happens? The force exerted on the bat ball. I think we have discussed that in detail. You have to use that concept to tackle this question. Okay, go ahead. Okay, let's see. Right, we have one answer already. Okay, let's see about the others. Right, another answer, similar answer. Okay. Anyone else? Two answers so far. Anybody else who got the answer? Come on. And both of them have got the same answer. Right, okay. Since we are running out of time, I'll start. Now, we have to, first, before we start the question, we have to understand what's happening here, people. I'll type it in. Now, water is striking the wall, water is striking the wall. So, according to Newton's third law, wall will give an equal and opposite force to water, correct? So let's mention that here in detail a little bit. Okay. A force will be exerted. The question is, what is the force exerted by water jet on the wall? A force will be exerted by the wall on water. According to who? According to Newton's third law. A force of equal magnitude. A force of equal magnitude will be exerted on who? By the wall on water. Exerted on wall by water in the opposite direction. Now we know the velocity of water. So let's first apply to water and find out the force acting on water, right? So water jet isn't some kind of jet in the sense it's like when you turn on the hose pipe, the water column like part coming out comes out, right? Very fast. That's what you call a jet. A stream of water, exactly. A stream of water. In a hose pipe, when you close the opening a little bit, water will gush out really fast. No? That stream is what you call a jet. Okay, right. Then let's start. First and foremost, before it recoils, water approaches the wall at a velocity of 5 meters per second. So that is the velocity at which water is approaching the wall. Okay, so let me show that this way. Water is approaching the wall like this through the tap. From the tap, water is approaching the wall like this, and that velocity is 5 meters per second. And after that, this is what I call the water jet, and that water jet is recoiling horizontally, same direction, not same direction, same line, but in the opposite direction, 3 ms minus 1. All right, and the cross sectional area of the tube is provided, that is 30 centimeters squared. 30 centimeters squared, which is 30 into 10 to the power minus 4 meters squared. 30 into 10 to the power minus 4 meters squared. I'm converting it to SI units. Okay, right. So this is our VU. This is our U initial velocity, and this is our final velocity. So to start with, for water jet, if not for water jet, somebody asked me what is a water jet. This is the water jet. For water jet, let's apply Newton's second law, mv minus mu over t. Force, and I have to define the direction, people. Since the final velocity is towards left side, I'm applying the equation towards left side. Okay, I'm going to apply the equation towards left side because final velocity is on the left side. Then force is equal to m over t into v minus u. Now, just like the previous scenario, m over t is who, people? Mass flow rate. MOT is mass flow rate, and the mass flow rate will be equal to, in this occasion, AU rho. Careful, AU rho, because this is the velocity or speed at which water is approaching the wall. So this much of water is coming towards the wall. AU rho. Therefore, your force is going to be equal to AU rho within bracket V minus U. Don't forget the direction. It's in this direction. No, opposite direction we took. It's in the opposite direction. Okay, right. Now let's try substituting the values. F equals, what should I substitute for A, people? F equals, for area I should substitute 30 into 10 to the power minus 4 into, for velocity I have to put 5, and for density I have to put 1000. Inside the bracket, what number should I substitute? 3 minus, what should I substitute? 3 in this direction minus 5 in this direction. Okay, I hope you guys understood that, because final velocity is 3 towards left, initial velocity is 5 towards right, so this minus is what I put here. Then I think when you multiply them, you will be able to get rid of few. 3 is 1, 2, 3, 4. 4 zeros will get cancelled out with 10 to the minus 4, which means F is going to be equal to what now? 15 times. Inside the bracket, you can make a change, that is 3 towards left plus 5 towards left, which is 15 into 8 towards left. So force is going to be equal to 120 Newton towards left side. This is the force exerted on water by the wall, because these changes in velocities are happening to water. 120. So I put 10 to the power minus 6 into 10 to the minus 4, but how did you get 72 over here? No, Zainab, it should be 5 here, not 3, because you have to put the velocity at which water is approaching the wall, because that much mass is coming towards the wall. No. You can't subtract like this, Ruksha. You have to change the direction, and you have to change the direction. You can't subtract them when the directions are different. Why can't we use 3 as the velocity? 3 as the velocity in the sense, okay, you can't use 3 as the velocity because 3, water is not approaching the wall at that velocity. Water is approaching the wall at 5 meters per second. So every second, area into this velocity rho times water is coming towards the wall, and that amount of mass is undergoing the change. That's why we have to put the initial velocity there. Got it? Because you have to see how much water is coming towards the wall, so that only comes here, how much mass is approaching the wall. So before the collision happens, this much water, how much water came towards the wall before the collision, that's what we have to put here. That's why it's AU rho. Okay, and the subtraction here is not something new to us, we have done it many times, or else you can do it in another way. How is that? Then people, wait, we'll finish this off. So force exerted by the wall on water jet is how much? That is what we have calculated. 120 Newton towards left. Then what is the question? Hence, force exerted by the water jet on wall, that is going to be 120 Newton towards right side. Sometimes in an MCQ they might give you direction also in the answer, so there will be both the answers will be available in the MCQ options, so we have to be very careful here. All right, there is another epic question. That question is based on this and rotational motion. Shall we try that? That's a really cool one. Okay, but before that I'll give you another separate question. Wait, I'll give you another question. That question I'm talking about is a question from support seminar. Now alternatively you can do it this way as well. Now you have come up to this point, people. You're going to apply F equals AU rho within bracket V minus U, and you're applying the equation in what direction? You're applying the equation in this direction. So F is what we have to calculate. Without putting the arrows, what can I do now? F equals A is 30 into 10 to the power minus 4 into 5 into 1000. And inside the bracket, you can put 3 minus 5. Can you remember this? Hope you can remember this. 3 minus 5. This minus stands for the direction. This minus stands for the difference. You can write it that way as well. So that will be F equals to 15 into 8 directly. F is equal to 120 Newton once again. So if you want to use the arrow, you can use the arrow. But remember, if you want to add or subtract two vectors, their directions must be equal first. Then only you can. Now here I can't subtract 3 and 5 because the directions of the arrows are different. So I have to first make the directions of the arrow same, or rather, directions of the arrow same, and then only you can add or subtract. I hope that is clear to everybody. Okay, right. So shall we try another one, people? Let's try another one. I think the next question I definitely must have seen in model papers. Let's start. Ready? Okay, start writing with me, people. Next question. Next question goes like this. Water flows through a tube and goes through a bend of 90-degree angle. With no change in the speed of flow. So let's assume that there is no energy loss happening, no change in the speed of flow. Velocity is going to change, right? The speed of water flow, was 27 kilometers per hour. 27 kilometers per hour, and I have to give you the cross-sectional. Cross-sectional area of tube was I'll make it easy for you this time, 25 centimeters square, because when you put 25, 20, 10, multiplication all will be easier, people, right? Find the force exerted at the bend by the water. Find the force exerted on the bend by water. Okay, what information is missing? Density of water, right? So density of water, as usual, we'll take it as 1000. Try to draw a diagram, okay, and apply the equation. Again, you can't say this is new to you. We have done similar questions exactly like this, and this time the confusion is not going to be there because it's the same speed, right? Do you think you can try, people? What do you say? Ship. And another one, density of water is 1000 kilogram per meter cube, and I'll say take root 2 equal 1.4. If you have root 3 in the answers, it's 1.7. These two numbers. Okay, so I'll give you a few minutes to try. Come on, just like the previous question, but we might have to think of a slightly different diagram here. Okay, Rima has come up with an answer and she says it's 140.6. Interesting. Let's see how it goes. 140.6. Anybody else? Any other answers? Please try. Okay, right or wrong, the answer's correctness we can talk about that later, but you just have to give an effort, put an effort here. Hurry up. Okay, time's up. I'll explain it. Okay, water flows through a tube and goes through a bend of 90 degrees. So from top, when you look at this tube, this is how it's going to happen, people. You know, bends and all like this in tubes. We call it an L socket or something like that. This is how the L bend is going to be. This is a bend. So we'll take the bend to be something like this, 90 degree. So what we need to understand here is water will be flowing through this path like this. Okay, water will be flowing through this path like this, and it will be, you know, hitting the wall, and it will start flowing like this after that. So water speed has changed 90 degree. In fact, I think this part I have to alter it a little bit, because this bend has to in fact look like this, then only it can change its direction, right? Like this. The bend has to be in fact like this, otherwise water will be unable to change its direction. This is how it should be. Okay, right. Now as you know, water, okay, first we'll convert kilometer power to meters per second. It's easier than first 27 kilometer power is equal to 27 into 5/18, no? 5/18. When you simplify 18 and 27, there will be a 3 here, there will be a 2 here. I'm getting 7.5, people. 15 by 2, which means 7.5 meters per second. So whenever I give the values in kilometers per hour, I'll always try to make it a factor of, multiple of 18 or 9. So this time I went with 9, 27. Right. So two of them have got the same answer, Hamdi and Rima. Let's hope for the best. 140.6 is that what they have got. And so water will enter the tube at that velocity, that's that speed, 7.5 meters per second, and it will be leaving the tube at 7.5 meters per second. Practically it is not possible, but it's given in the question, so let's go ahead with that value. This time the direction of velocity is definitely changing, but in the perpendicular manner. Okay, perpendicular manner. Right. So let me quickly go back to the equation. What is the equation, people? Force equals mv minus mu over t. Now I can't put an arrow here for force, because the direction of force, the direction of velocity is not just horizontal or vertical change. So I'll just leave it like this. Force is equal to, again we can take t out, which means I have v minus u. Okay, then for m over t, once again I can substitute what, people? Au rho into v minus u. Right. So F is equal to area. What is the area? 25 into 10 to the power minus 4 into initial velocity or initial speed is 7.5 multiplied by density of water is 1000. Inside the bracket now you have to be very careful. V is the final velocity, that is 7.5 downwards minus 7.5 to the right. Okay, then here 10 to the power minus 4000, so it's 75 into 20, 0.25, something like that. So F is going to be equal to 18.75, no? 18.75 multiplied by this one. Now there is going to be a magnitude there. Hope you can remember from our vectors lesson, people. When you have, oh wait, I have to change it, right? So it into inside the bracket I will put 7.5 down plus 7.5 towards left. So according to the vectors lesson, we know this is how we find the resultant. How is that? 7.5 down, 7.5 to left. This 7.5 ms minus 1, the velocity, and here 7.5 ms minus 1. People, what is the resultant? Resultant is going to be along this direction. What is the angle created? The angle created definitely is 45. And this is going to be how much? When you have equal magnitude of vectors, this will be 7.5 root 2. 7.5 root 2. That is the resultant, magnitude of the resultant. So you have to say f is equal to 18.75 multiplied by 7.5 root 2. Okay, people. F is equal to 18.75 into 7.5 into 1.4. Unfortunately, there are too many decibels to deal with, right? Let me change it now. 18.75 I can convert it to something like this. Now it will be easier then. It is in fact 75 by 4. Do you agree with me? 75 by 4 into 7.5 into 1.4. Will it be more or less the same? No change, ne? There's no big difference, I think. More or less the same. So 4, it will be 2 here, and it will be 0.7. More or less the same, people, unfortunately. Okay, so since there's no point of changing that, I'll directly multiply all 3 of them. F will be equal to, you will correct me if I'm wrong. I hope I'm not missing anything. Euro A. People, I think I made a mistake. Did I make a mistake here? No, right? Yeah, no, I'm correct, right? 18.75. Unit conversion, what to explain in the unit conversion? Unit conversion, you have to multiply, like, I don't know, you can do it this way also, Zuhara. We have learned, we have used it many times before. Unit conversion is like this now. Are you talking about the green color one? This one. 27 kilometer per hour means 27 kilometer in 1 hour. So that is 27 into 1000 meters over 1 hour means 1 into 3600 seconds. So 27 into 1000 over 3600 is 5 over 18. That's how we got this. Simple. We have used that many times now. Or maybe you didn't join the class at the beginning, I don't know. This is it. So if you use 5 by 18, it's very convenient. Very convenient. Okay. Okay, then we'll have to multiply these 3 numbers. What are we getting, people? 7.5 into 1.4. 7.5 into 1.4 is how much? 18.75 multiplied by, I think, 7.5 plus 10.7, so 10.5, 10.5, I think, 10.5. Yep, 10.5. Yep, 10.5, and then I have to multiply 18.75 by 10.5. 18.75 by 10.5. 18.75, 10.5. 5 into 5, 25, 2 balance, 7, 3 balance, 3, 4 balance, 9. Nothing here. 5, 7, 8, 1. People, I'm getting 5, 7, 8, 6. I'm getting the final answer, which looks like this: 196.88875. 196.875, which is equal to 196.88 unit. Okay, almost all of you sent me an answer which is 140 odd something. Why? What happened, people? Okay, 7.5 root. How do I say 7.5 root 2? Right, let's explain that. That also we have done under vectors. But never mind. Zuha also joined the class a little later, I think. No, not Zuha. Zain, Mariam Faiz. Imagine you have a what do you call that? You have a right angle triangle. This is x, and you are supposed to find y. So what is the equation for y, Mariam? y is equal to x squared plus x squared square root, Pythagoras theorem. So that is going to be 2x squared square root. Okay, so when you take square root of this, square root of 2 is root 2, square root of x squared is x. Okay, so it's the one that's how I got that. Is that clear? So in future, when you get two vectors which are equal to each other, we can use this. I directly use this because we have used that many times in our previous questions. Right, so all of you have made the same mistake. Everybody. Now Zainab Nazar, Avasha, Zainab, who has got Zainab, no, Hamdi, Rima, Hamdi, Avasha and Zainab Nazar, you all have got 140.6. Can you figure out where you have gone wrong? Yeah, direction is not necessary. If they ask, it would be better to mention. No? So the direction will be this. This will be the direction along the diagonal at 45 degrees. That is how the direction is going to be. I use the equation AV squared rho. No. You can't do that. You can't use AV squared rho here. I told you from the beginning, you can't use that equation directly. Please draw a diagram and this. Right, that's the mistake, I think. No, sorry. This is the force created by bend on water. This is the force created by bend on water. Yeah, that's not what they're asking. No? They're asking for the force created by water on bend. What I have calculated here is the force created by bend on water. Okay, so I think we have to clarify that. I'll say these are the changes happening to water. The people who is making that change happen to water, the bend is giving a force on water. So I'll say force exerted by bend on water, that is equal to that value 196.88 Newton in this direction. So force exerted by water on bend, on bend, that is going to be the opposite. That is 196.88 Newton the other way. Okay. Yeah, okay. So Avasha has forgotten to multiply that by root 2. People, don't worry, these things can happen. Let's be mindful in future. Right, so I hope you learned something from this question. So two questions in two different approaches. That's why always putting a small diagram like this always helps people. Even here, when you put a diagram, then you will not miss out on things. Good. Right. Let's move on. So the equation F equal AU squared density, you can't use that. Now, Hamdi, didn't I mention specifically you can use that equation only if the fluid is rest initially or if the fluid comes to rest finally. One of these two velocities must be 0. Then only you can use this equation. Understood? But in both the situations here, the final velocity was not 0. Initial velocity was not 0. Sorry, here it was 5 and 3 in the opposite direction. Here it was 7.5 and 7.5 perpendicular to each other. That's why we can't use that equation directly. I hope that's clear to you. If you want to use AV squared rho for force, one of the two velocities must be 0, people. It could be the initial velocity or the final velocity. Okay, so shall we add that point here? I don't know whether you have written it. So can you do a question whether fluid is at rest? Oh yeah. That's what we are going to learn next. So near this, let's add a note. This equation can be directly used only when one of initial or final velocities of the fluid is 0. Is it clear now, everybody? So let's be mindful about that. Okay. If there's a change in direction, you go back to Newton's second law and do it like we did questions in Newton's second law. Okay, then let's move on to the next one. Now I'm going to teach you that special case I was going to explain, but before that, shall we take a short break? Take a short break now, Riva. 44, or else, yeah, we'll take a break now. I'm hungry. We'll take a break now till 9, and at 9 we'll start and continue for 1.5 hours and finish. And I'm going to teach you how a helicopter operates. So we're going to learn next. Okay.